Hi everybody and welcome to Western Idaho, the Western Idaho Shear Zone to be specific, and the Penrose Conference, run by Basil Tikoff, University of Wisconsin. I hope that you enjoy this field video. It is Saturday, August 19th, 2023, and there are 75 geologists who have flown in from all over the world to enjoy the Western Idaho Shear Zone, the rocks, and a chance to contribute their knowledge and the debate of Baja BC, oblique subduction, Western Cordillera, whatever you want to call it. It's an exciting week and you are invited. Thank you and let's get started.
Smaller, and so we're able to observe them using our Biasi kind of picturing all of our specimens. We also wanted to look at any of the additional variations. So for our magnetic technique, we often observe purely magmatic titanite within these photographs, as well as these very partially recrystallized, microstructurally occurring sort of recrystallization. Okay, I am open to any and all questions. I said that very fast, but this was my baby.
Sarah, what was the initiation age?
Oh my goodness. Initiation was between 96 and 98 MA. My goodness. There we go.
Good question.
So this is all from just one site within the Little Goose Tree. So we weren't really going straight for that finite frame, but that's a huge part of the story.
Well, we got just a few minutes before we're jumping in the vans, but here's a familiar face, Stephen Johnston. How are you?
I'm good.
Thank you for coming all the way down from Edmonton. Are these kinds of rocks familiar to you? Did you work on stuff like this way up north someplace?
These are familiar rocks, yeah. We have same age metaplutonic rocks, deformed intrusions in Yukon, which we call the Omanika magmatic belt. And this looks a lot like a lot of those, kind of intermediate color,
Yeah.
biotite, sometimes biotite muscovite. These beautiful sheared porphyroclasts of feldspar. Yeah, so it's
Huge dominoes, yeah.
yeah, that's right. And so they're hard rocks because there's been a lot of debate about how much of the fabric is plutonic, so magmatic flow, how much of it is tectonic, the timing. It seems like intrusions are always closely followed by deformation. So the timing gap between intrusion and then the deformation, like in these rocks, not very big. Yeah.
So you say Omanika, what are a couple field spots that you feel very comfortable with plutons and then deforming the stuff shortly after?
I worked when I worked for the Yukon Geological Survey. I mapped out what was called Big Creek Fault, and it was a strike slip dextral fault that had associated with it what we call Dawson batholith, and Dawson batholith turned out to be Middle Cretaceous, just like these.
Ah.
And you could walk the fault into highly sheared gneisses, very much like these rocks. Yeah.
But we can't connect the dots. We can't easily just march from Yukon down to here and know where we are.
No, and one of the conversations I've been having here is how different it is here in terms of topography and geology than it is just 500-600 miles north in southern British Columbia.
Yeah.
You know, so I've taught field schools over and over through southern British Columbia, and I'm just aghast at how different it is here, such a short distance south. So to try and go from Yukon to here, it's a bit of a leap.
All right, well, we can cut this part, but just why not? So in your worldview, this is all exotic material. We're all in the ribbon continent, and we have to go how many miles or kilometers to the east before we get to old North America? We got to go into...
Yeah, we have to
the
go
belt.
east. Yeah. If these rocks in Yukon, I believe intrude a ribbon continent.
Okay.
Paleomag from that ribbon continent says it's moved 1,900 kilometers north. So actually, if we undo that 1,900 kilometers, those Yukon rocks would have been just south of here. So
Wow.
that would push these rocks, obviously, that much further south.
Yes.
Most people justifiably have a hard time with that because these rocks seem to intrude and be associated with rocks that are North American, just, vanishingly small distance to the east of us.
Yeah. So why are you here? Do you have a couple of specific hopes for this week?
I want to learn what the geological ties are at this latitude. I want to compare the story that they've generated here with the geology I'm more familiar with in the northern Canadian Cordillera, and I want to try and find a way forward.
Good.
I mean, I am not questioning 20 years of detail, very detailed schematics.
It's got a glacially washed one.
But it takes a great big.
This block we take home?
Oh, yeah, right.
Dude, I'm kind of just interested in having
Shortening, pure shear, and then more so with time. And so that's dominated by pure shear. And then Basil would argue, example of pure shear eventually dominates. It's high enough so the fact that, again, it adds the ellipses progressively. If they're rotating, it's not as long as when you're just doing it in the same sense. So that's why we should be looking these should be dextral on this surface and more or less mixed on the same surface.
Can you show me a dextral surface?
You have one. There's a lot of experiments where
so you want whatever's pointing right at so you read the top here, so it's about 5. If you have it reversed, like if you're measuring it like this, then you have to read the bottom view.
That's where I like.
So there's a little more thinking than the regular to make sure you're reading it right. But yeah, that would be different.
Oh, that's helpful.
And then for trend and plunge, really just take this edge along the, if that was a lead. You have to keep this rotated part flat. You have to keep this marker tilted. Well, sorry, for striking dip, it has to be flat.
Any sort of like really steering that makes tails. A lot more rotation. I'm a bit
Right. Or I guess the blade, yeah.
No, that's hard to me.
I'm sorry, what were you typically was it transvestite?
Yeah, for class. I mean, I like it. It's like,
Yeah.
I mean, I bought it.
Like whiz bang everywhere. What convinced me is when you get the dikes, they're always folded like this, and they're always elongate like this. And then you get the stage shear zones, and they're always and then you're like, and then we did sort of the statistics of it clearly.
So when I was that brain drain so much.
Yeah.
People estimated the amount of displaced territory.
That's right.
Because it's so hard.
It was 100 volts. Yeah.
Is this guy Georgia?
This is George's. Yeah.
And so
That's what I.
how long
When I put it in, feel like
He actually covered the Little Goose Creek pretty well,
people were.
but the porphyritic goose is
collaborating
what you
with
need.
that.
There's a non-porphyritic phase over there. You can't do it. You can actually put it on paper. And so you can see sheared Bay River light, and you can make the same kind of estimate. That he actually has a plot in 2017 paper.
Also, some really fun Titanites. We heard earlier about Sarah, who was doing some Titanite work, and you can see why she was able to do such awesome mapping of them.
Oh,
They're
yeah.
huge crystals.
These little brown guys.
Yep.
Yeah. And what did you gather from Sarah about what she was getting out of those Titanites? Why were those important here?
Well, it looked like she had quite a spectrum of ages, showing the timing of the shearing.
Okay.
And we've also had some experience with Titanite ages showing some cooling. So, the zircon will be a little bit older than the Titanite ages, so slow cooling plutons.
Yeah. So you're working currently on a PhD with the Idaho batholith?
One of my projects is going to be on sediment in modern rivers that's coming out of the batholith.
Oh, that's right.
Yes.
That's right.
So we're going to constrain some chemistry on all these accessory minerals.
Cool. Oh. Let's do one more. So,
I agree.
why did you come to this conference, and what are you hoping to get out of it?
So I'm finishing up my project on the Gold Beach terrain in Oregon, and it's a player in this whole Baja BC translation. It looks like it's got an origin in Southern California, so we're doing work there and making it fit up here.
And you're going to share that stuff with everybody
I
this
will,
week.
yes. I have a poster on Thursday, I think.
Cool.
Yeah.
Thank you, Ericka.
Thank you, Nick.
So we're here in the Pay River tonalite, but most of my kind of microstructural characterization and uranium-lead work was done in the Little Goose Creek complex. And so what we are trying to do within these units is essentially say something about deformation initiation. Little Goose Creek, we've been able to constrain the end of shearing within the western Idaho shear zone within that unit, but it's a little trickier when we're trying to tease out, okay, when did deformation start?
Sure.
And so the chronometer that we leaned into very heavily, both myself and Claire Harrigan, we are two parts of a whole in this, so she's, I wish she were here with me.
Yeah.
But essentially, we went through, we sampled pretty much from one unit within the Little Goose Creek, and we collected tons of Titanite data. And so my work was essentially, do we see any patterns in these Titanite data? Can we identify any sort of specific morphologies? And so some of that was done just classical optical petrography to begin, but then we went more into our backscatter electron imaging, and then EBSD. And so from there, we were able to characterize 5 different main populations, some magmatic titanites, some partially recrystallized titanites, an early generation of neoblastic growth, these beautiful boutonaged lays that are parallel to that very steep foliation fabric, and then also our late stage neoblasts. And so from all of that, and all of that dating and all of that characterization, we felt comfortable doing the ID TIMS work. And so from there, we were able to determine both the deformation initiation age using both the microstructure combined with the LAICPMS data. So just really getting that chemistry nailed down, which fully supported what we observed microstructurally. So
say it's a 120 million-year-old arc, and that goes through the intrusion of this stuff, the Little Goose Creek. So from 125, my world, to 120, there is a subduction zone offshore, somewhere out from the Wallowa terrain, that's giving you a magmatic arc. There, I do not know whether that subduction zone has gone. The usual answer is north. Then that magmatic arc is hugely shortened in the western Idaho Shear zone, and you continue to intrude the Paya River tonalite during the late stages of that at 91. The Paya River tonalite, which is the only unit that is continuously in the whiz. The other units that are involved in the whiz come and go. This porphyritic granite you lose as you go to the river. You just don't see it in the river, but you see the Paya River tonalite. You see the Paya River tonalite here. You see it down at Say-10. You see it down in the Oahe. You always get this late Paya River tonalite. So it goes for about 300 kilometers. Then the Idaho batholith comes in. What is that? I don't think this is an arc-related batholith. I think this is a plateau-related crustal melting. There are all the xenocrysts are inherent, all the zircons inherited here. Basically, they're all cores. They're all tumica. It's a sea of tumica granite out there. That's late Cretaceous to Paleogene, so that's during the contractional event. The Columbia River basalts come up, and then they locally they concentrate in the whiz. But that's basically what's going on, and that's because of out of the plane rotation. And so it's one of these things with this whole topic that we're talking about. We do things in map view, we do things in cross section, but neither one is actually satisfying. The system is so three-dimensional. There's things in and out of the plane. Different parts have joined with different parts at different times, right? So it's complicated. The other problem is, if we're right that this is a ridge transform, if you look everywhere else in the Cordillera, the extension is on 330 trends, and the transforms are on 060 trends. The only place that's not true is Idaho. So, and the paleomag we have from this Paya River tonalite equivalent up in northern Idaho says after 85 million years, 90 million years, depends on how you want to interpret it, about then, that this had to have rotated 30 degrees like this. The Blue Mountains also are consistent with a 30 degree, it's a 22 degree rotation between 90 and 55. Is that right, Bernie? It's about then. Yeah. So we know the Blue Mountains are rotating. The Blue Mountains, there's no extension that we see between the Blue Mountains and the Whiz. And so if the Blue Mountains rotate, basically Idaho's got to rotate, and that's at least confirmed by this. So that's a hypothesis. We don't really know, but boy, does it make a lot of things kind of fall into place in this zone. The only feature that can accommodate that is the Lewis and Clark shear zone, which seems to be sinistral till about 50, and then after that it goes dextral for reasons I don't want to explain at the moment. But there's a phase where you get the extension, because 55 is a major age. So as we come through here, to me in Idaho at least, 100 is a major age. We see a lot of stuff going on. 85 is a major age. The arc stops doing it, and you have to push strikes up elsewhere. And then 55, I think, is well recognized as this other age as you go from contraction to extension, at least the northern part of the Cordillera. So,
Gene Humphries, University of Oregon, how are you today?
Doing well.
Good. Well, we got a few minutes to walk back to the rigs. You've been at this a while. What is your specialty, Gene? What have you been producing over the years?
Well, like to use geophysics and imaging in the mantle, combine it with what we know is going on at the surface, and make stories for what's going on.
Excellent. And I haven't involved your work necessarily with some of our discussions this past winter, but I am thoroughly familiar with your work. Were you the first to find a slab down below Idaho?
Essentially, yes.
Okay.
You know, product basically of the timing with Earthscope coming through.
Yes. And did you have instincts before that line that was there, or was that just a complete shock that slab was hanging there?
Now, earlier there were clues from a few stations that there was something fast there.
Okay.
And not being able to image it, I confess I mostly just kind of ignored it.
Okay. And how regionally significant is that? Did you call it the Idaho slab, or somebody else monikered that?
I just call it the Idaho curtain.
Idaho curtain, yes.
Yeah, you know, you see it, it's a slab that's come off as ocean lithosphere. It's formed where it's cool, near the surface of the earth.
Yeah.
And then you gotta make a story for it.
Right.
And the story I like, and can argue for, it was flat slab, all the way under Oregon and under Idaho and under western Montana.
Mm-hmm.
Okay. And then when Silesia accretes, that whole piece of ocean lithosphere stops moving. We start subduction outboard at Cascadia now. And once that happens, the slab peels off or delaminates from Montana heading west. And as it does that, it exposes the plate, North American plate, to the cenosphere, and you get the Chalice, Ericka, that kind of volcanism.
So we have you here, we have Johnny Wu here, we have Karin Siglock here. You guys are all approaching things. It appears, I don't understand why there's such a major difference between your views about what you see at certain levels. Is there a simple way that you can describe that? Is it?
Yeah, well, I'll tell you, you know, Karin is kind of I'd say a really good, maybe the best seismologist running around these days for imaging that scale.
Yes.
Okay, using global data. I use arrays distributed around the Pacific Northwest, for instance.
Okay.
And I think I have better imaging of the upper 500-600 kilometers, and especially as you bring it towards the surface.
Uh-huh.
So the same structures, and it'd be interesting to try to come up with a joint model of all that.
Right. Are you then comfortable speaking mostly towards Pacific Northwest issues as opposed to Rocky Mountain issues or Cordilleran scale stuff?
I love the Rocky Mountains.
Okay.
Yeah. And I'll talk a little bit about that tomorrow. But
okay.
In my view, you're more about flat slabs.
Yes.
To me, it's Ocean Plateau, which I'd say is a Shatsky conjugate.
Okay.
Subducted under California, under the Colorado Plateau, underneath northwest Colorado, and it's still residing now, abandoned beneath Wyoming. Okay, and in the process, under the Colorado Plateau, it coupled enough to drive the Colorado Plateau towards the continent, causing the Rocky Mountains.
So the northward translation in the Baja BC story does not work in your view? Is there a way that some of that northward translation can work with your views of?
Well, we'll find out at this meeting more, but I could argue strongly for flat slabs, okay, based on our imaging, tectonics, blah, blah, blah.
Yeah.
Baja BC seems to have some good supporting evidence. If Baja BC is right and flat slab subduction is right, then you gotta make them work. And you kind of can. It requires, getting the timing right, getting Baja BC not too far south at 85 million years, for instance.
Yes.
So you could sort of make it fit. I think with a little consideration, it probably all fits.
Good.
Okay. And it'd be interesting to talk to George Garrels a little bit about that too.
Absolutely.
But this meeting is great because this is kind of an important tectonic problem to many people. And I think here we may actually, if we don't solve the problem, we'll certainly define where we have to go.
That's perfectly said. Thank you, Gene.
Sure, thank you.
Rebecca Morris taking a photograph.
I'm falling behind the group. This is
It's worth it.
too cool.
Okay, it's mid-afternoon on Saturday, and I hope that you can see why people have flown so far to get to a place like this. Look at these gorgeous rocks. These sheared rocks, these formerly simple plutons that have been deformed to create these gorgeous textures, these fabrics. And we have experts from many different disciplines here to contribute to this discussion. As I've mentioned, I need to be careful with how I report on this conference. So many of the detailed discussions will be away from the camera. But I do want to give you a sense of what it's like to be on a conference with these folks. And if you look carefully, you can see some glaciated, sculpted, metamorphic rock here in western Idaho, and the geologists are just descending.
Salmon River, the early Cretaceous Salmon River event. They're on the North American side. They were formed by Salmon River, belt, that early Cretaceous stuff, and then they stopped. And then there's a second big inundation.
Don't see anything wrong.
And then they're formed by the wind.
You're not doing
Much more overwhelming by the wind.
That's the best conversation.
Holy cow, this is stunning. Oh my God.
So there it's more, it's the bigger thing, the bigger deformation is the wood.
So this more strange day that is arguably locally less.
Okay, Stephen, you've seen something here. You've mapped a lot of stuff. You've never seen something like this, huh?
Yeah, this is quite incredible. So you can see this highly strained gneissic rocks.
Yeah.
And right here, if you follow along, you can see this one strain zone starts cutting through the layering.
Yeah.
And it's quite ductile, and it's got little bits of pegmatite associated with it. And as we come up here, you can see it's kind of bifurcating, and then suddenly it goes brittle. And you get these brittle faults that are truncating, and it's best displayed right up here where this layer is cut and faulted several times on this one shear zone.
What in the world?
Amazing. Just beautiful.
So that's, I don't understand, because I thought we were so deep beneath some sort of brittle zone that we would have nothing but ductile down here. How do you explain having both styles in the same?
Yeah.
Do you think there's different ages involved?
I'm totally at a loss.
Yeah.
I would think,
Yeah.
because it's got this little bits of pegmatite, okay, it looks like there was fluid in the system. And one way it could go from somewhat ductile to brittle is if you have a fluid-rich system that's flowing, and then suddenly you lose the fluid, then it might go brittle.
Huh.
Yeah. So,
I mean, in central Washington, I'm familiar with myelinites.
yeah.
Would you call this a myelinite? What would you call this?
No, I don't see any myelinite here. And in part, I think that's because there's strain being taken up by liquid. So instead of getting very strong, and I mean, these rocks are quite deformed, but not only are they deforming, but they're recrystallizing fast enough that you don't get the grain size reduction that gives rise to myelinite.
Okay.
Yeah. So myelinites, you have to have a situation where the grains are breaking down smaller and smaller and smaller until you get just to that almost flour that's been textured.
Yeah.
Mm-hmm.
Well,
Yeah.
There's so much I'm blown away by here. I don't know if I've seen such a spectacular outcrop, just aesthetically to have.
Yeah, it's very beautiful, isn't it?
Huh.
And you can see these little little shears here where you can just see all these little hornblends are bending up into this little feldspathic pegmatite. So there's nucleation of shears along these little intrusions.
So this kind of thing you have seen up north?
I have seen in general this kind of package of rocks, this kind of synmagmatic deformation. Yeah.
Okay.
Yeah. So, but this is quite spectacular. Absolutely.
Thank you. Margi, would you be willing to talk for a couple minutes on this camera thing?
We were just looking at one over there that was like, oh, look at this.
And then it's intruded
Yep.
by this late fabric here, by this late.
See, now you have to.
If you don't mind, Margi, I mean, you have.
I was really the one. How I approach them is to try to sort of look through them systematically and say, well, are there different types of rocks and what sort of deformation are each of those showing? And is there a consistency of that deformation based on rock type, and can I deduce what we call the kinematic view?
Okay.
Which way do we want to be looking to see if we can understand the direction of the shear zone?
Oh, I see.
And I'm absolutely not sure here what is. We see a lot of sinistral indications in this flat view, but I don't know if that's it. But we're also seeing a lot of folds. See that one that comes up and around here? So this is what I sort of see as a stripy zebra unit. Okay. That's a technical term. And it'd come around, and it looks to be folded here, and then it goes back like this. And then it goes back and is folded again.
Oh, no kidding.
Here, I think. Not positive, but I think so. And then it's got a younger phase. So I just try to pick out the different groups of things. And here's a fold in the, or it's intruded across and been shortened. You don't know whether that's actually folding, but it looks like a fold. But then this phase, I've seen this fine-grained intrusive phase in a lot of places here. And over here, it actually chops up the stripy zebra.
Yeah.
And so one thing that, you can see here how this has got this nice viney, so it's got a foliation to it that's being cut along this margin here. And so one thing that I would do is say, well, can we get any age out of this? Can we date this piece? Can we hammer this out somewhere and date it so that we at least know, and date this, we would at least know what the range of deformation is. It obviously the deformation is after this and before this. And then you can look at at this fabric. It's a high temperature recrystallization fabric. Most likely these are biotite and hornblende that have recrystallized into these long stringers. And so you'd want to look at that in section 2. Here's a nice little piece of this stuff that got sort of engulfed or maybe overlapped by that. So this is, unraveling an outcrop like this is really very time consuming, and it's not necessarily the most effective way to study a big 10-kilometer wide shear zone. You just might not have time. And so that's my situation. I work in really remote areas. I've got a helicopter schedule. So sometimes I'll just come to this, I'll photograph it, and I'll say, this is what I saw, and hey, maybe we'll come back and do a detailed study in the future. But I need to sort of get my head around the whole shear zone and not focus on the most complicated parts. But this obviously has a long high temperature history and is a very beautiful outcrop. And that's sort of all I can kind of pull together, Yeah, I'm going to talk a little bit about that I'm giving an overview talk, and I'm straying a little bit from the total overview so that I can talk a little bit about the coast shear zone, because I think it's important that we understand what that batholith is and what it isn't. So, because it is on the zone between what have been called two very large continent scale blocks. Which is what Basil asked me to talk about, and then I'll talk about the stuff I want to.
And how are you feeling about taking that coast shear zone and lining it up with this thing down here?
Well, the timing's wrong. One of the cool things about the coast shear zone is I think we have evidence now, which is unpublished, so my colleagues may tell me otherwise, but I think we have evidence that it starts at 72 million years. And this stuff is 100 to 85.
Yeah.
That same period, 100 to 85, in the coast mountains, we have shortening, contraction. It's talking about big folds and thrusts on the west side of the coast shear zone. And that's exactly the same age as this period, where we've got some squishy transpressive stuff, and then it runs into the elbow and becomes contractional at the same direction. So that's interesting.
Yeah. But so young compared to.
The Coast isn't very young. It's much more. It's what it is, Nick. Is the start of that whole Yalakum, Chakazan, Castle Peak, the whole Cascades, Entiat, Ross Lake. It's the start. I think it's the oldest in that. Or those started then, and we just Bob Miller and I have been talking a lot about those. May have started at 70. We just don't know. So I actually think we're starting to see a signal that's older, and it's probably. Its abrupt inception probably tells us that we have some reorganization along the plate margin, perhaps a shift in plate vectors or something. So,
very cool.
So we start. That is when we really start to move stuff. But how those connect to down here, I've been trying to. I don't know. That motion has to come through here, and it has to go through the Cascades.
You're right.
I don't know. So, a long, hot afternoon.
Right.
All I can say is I don't know.
Thank you.
Yeah, we saw something like that down below, but it was
Yeah.
Okay, I think I'm going to move us downhill again. So the next stop is a bit of a ride, maybe 30 minutes, and we're going to see the Paya River tonalite. So we're finally going to get over to North America. There you are. Okay, so make your way back to the van. We need to go through immigration. That's.
And just like go off this side. He's like, yeah, so I think it takes like 20 minutes to get down there. Did you guys take the wall the way back?
Michael, take the flagging off. Thank you.
Okay, everybody. Well, this is the Western Idaho Shear Zone. If you were with us this winter and we were talking with Basil Tikoff numerous times about the Western Idaho Shear Zone and its significance with regional tectonics, Basil has taken this group to these outcrops, and many of them are quite impressed. You can see that the landscape is sculpted by ice, but that is not what we're thinking about. There's no J. Harlan Brett's discussion here. Instead, these are incredibly deformed, formerly simple plutonic igneous rocks that have now been squeezed and sheared. Transpression. Hands coming together and also hands shifting sideways. So it's like, what does it look like deep beneath the San Andreas Fault in California? If you go down deep enough beneath the San Andreas, you're going to see rocks that look like this. They are hot, they are under a lot of pressure, but they are still being shifted in that hot, pressurized, gooey mess. Wonderful. Looks like we're heading to the next outcrop. Hope you're enjoying this little field trip.
Same summer, and it confused the hell out of me. She did better with it than I did. So anyway, this is Snowbank Mountain right here. That's where the migmatite is, and on the scale of this map, Sagehand would be about there. So it's all on this west mountain block, right? And that's where the seismic line, the Idaho seismic line that I showed yesterday, and I could show again here, but it basically goes right across here. So this is where we know that the Western Idaho Shear Zone at the surface goes straight down. and then offsets the Moho with it deeper on the North American side, shallower on the Olds Ferry side.
Basil, is there any barometry on this tonalite?
Right, so we did quite a lot of aluminum and hornblende barometry. Nobody loves that barometer. I think it's amazing. Hornblende's useful for anything. So we did a lot. It lines up.
Cut.
Well, it's like a hornblende support group here. Right.
Interestingly, I published on it.
Hornblende's been good to me.
Hornblende's been very, very good to me. Okay, so here we are. And it's everywhere about 5.5 kilobar with this stuff. And it's surprising, I mean, again, because it goes all the way to the Oahes and all the way up, it's 5 to 5.5 everywhere, right? The mineralogy is the same, the depth is the same, the age is the same. It's stunning. I have no idea why the hell it happens. But does anybody at the coast range want to talk about why the Great Tonalite Still happens? You really to go out on a limb on that one? Okay, great. Margie says look at the rocks.
So you have to erode 20 kilometers of
Yeah. Idaho gives.
Well, when you say it's 91.5 plus or minus something, you think that's a great question. How much of it is? Well, I don't know. All I know is we dated in the Oahes, we dated it South Mountain, we dated it here, and it comes up exactly the same age. So if you really want to be systematic, you'd have to go through. But it's like it's stunning that it's always, it just comes in within error bars of each other. It's really weird. And so it runs for 300 kilometers more or less. The Great Tonalite Still runs for a couple thousand kilometers more or less. I have no idea. This is a fundamental process. What's interesting is the Great Tonalite Still is, what is it, 55, 58, something in there. And this is all, yeah, okay. So six. Right. That's right. That's running along crustal break, and that's the end of the shearing. And that's what we have. All right. Look around. Pay River Tonalite. Look around. The shear zone's at the top of the hill if that's of interest. And then we'll be done.
No, I'm still working remotely. Are you sure? I don't know from home. But where is the? I'm working on
It's north.
Joe, pleasure to meet you.
Good to meet you too, Nick.
You're just starting at the University of Wyoming. It's not just you, though.
Yeah, it's not just me. We made a couple hires this year. So I'm starting as an economic geologist, working on ore deposits and things like that. And then they hired my wife as a petrologist, and we make a dynamic duo, apparently.
Okay.
Yeah.
And why are you here on this conference?
Oh, that's a good question. So the conference deals a lot with the tectonics of the Western U.S., and that's something I've been thinking about for 10 plus years now, basically. Okay. So I don't really have a big stake in the game, but I always want to know more about it. Sure. And see what other people think about it and things like that. And these small conferences are a great way to meet other people that are really like focused on the same things that you're focused on. So it's a lot nicer than some of the larger conferences where you can just get lost in the crowd, you know.
You have done some paleomag work?
Yeah, quite a bit around here.
Okay.
Yeah.
Let's hear more about that because, you know, this past winter we were hearing about Merle Beck and Bernie Hausen and others who've amassed a bunch of paleomag work, Randy Inkin, these fellows, Stephen Johnston, but you're a younger guy and you're doing paleomag.
I am, yeah, one of the few.
Okay, yeah, well, right. So what paleomag studies have you done over the last 10 years?
Yeah, so most relevant, at least to this conference and this Baja BC issue, is I've done a lot of stuff in northern Alaska. Basically, you guys may have heard a lot about all these terrains or these packages of rocks that are getting transported north, but they eventually have to run into something, right? There has to be a backstop somewhere, and people have sort of ignored that part of the equation. Where do these things eventually end up? Where do you eventually find rocks that haven't moved very much at all? And that's an open question, basically, that I'm currently trying to investigate. is how far north do you get before the rocks are sort of stable, they haven't moved too far and stuff like that. And what I think is quite a bit far north, maybe the very middle of Alaska or farther north than that, is the last bit of terrain, bit of rocks that haven't really moved very far.
Sure.
Yeah.
These rocks here,
Uh-huh.
do you have any specific interest in the Western Idaho Shear Zone from what you know, or this is just a general learning experience for you?
You know, this is a new area to me, and Basil's been running a really great trip so far, and I asked him hundreds of questions over the last hour when he was trapped in the car with me, right? So one thing I'm very interested in is this tonalite right here that he's been describing, where he says it's very, very long, about 300 kilometers long, which is extremely unusual for a single magmatic intrusion. And he's pretty confident that it's a single magmatic intrusion because it all has the same age, about 91.5 million years. And so the reason it's very unusual is because the magma is pretty felsic, and it's really hard to make a lot of felsic magma at once. It depends on exactly what you believe about petrology, but the general thinking is you have to start with a mafic magma, then you differentiate it to make a felsic magma. So for every 1 part of felsic magma, you needed to have 10 parts of mafic magma originally.
Yeah.
So anytime you see a whole lot of felsic magma at one spot at one time, it's very hard to make that and very unusual. So, at least inspired by this trip, I might work on this going forward, me and Basil.
Yeah.
Yeah.
Well, and he's not saying this was a big blob of magma that was then compressed to make the shear zone. He's saying that it squirted up, or it was liquid coming up a kind of a tabular body.
Yeah, it was coming up during the active period of the shear zone. So the shear zone goes 100 to 85 million years ago, and this is all 91.5 million years ago. So while things were sliding past each other, this magma was coming up through the cracks. A whole bunch of it came up all at once. And those things are very unusual in the geologic record, to get a lot of magma all at once. Yeah.
What might you add to this? Or what, if you collaborate with Basil here, what's your expertise to help? He hasn't really had a petrologist working?
He hasn't really had a petrologist working on it. So there's two things. One is, how do you make this much felsic magma all at once, right? This is actually a bigger issue than just in the shear zone. This is a big debate in the volcanology world. Some of your listeners may have heard of super eruptions and things like that, where these enormous, enormous volumes of magma or lava come out of the Earth's surface. And we don't really know how those happen at all either. People think there must be a bunch of felsic magma below the surface, but no one can really find them until you get to places like this, right? Where this happens to be a big exposure of a lot of felsic magma. So this has some super eruption connection, but so one is, where did the magma come from? Right, that's one thing I try to figure out. You can do that mostly using geochemical techniques. So you can do major elements, minor elements. We're talking iron, silica, potassium, sodium, things like that. And then you can get into certain isotopes, like strontium isotopes or neodymium isotopes, are very good indicators of where the magma came from, whether it came from melting of the crust or maybe deeper down in the upper mantle or something like that. So that's one thing I would want to do. And then I do have the paleomag connection. So when you date a pluton or a magma body and it all gives you the same age, that's within error of your measurement. So maybe your error is plus or minus 100,000 or 200,000 years. You can also try getting a paleomag direction from different parts of the rock, right? So let's say if I got a direction north of here that pointed 30 degrees east, and then I drilled here and I got a direction that's 30 degrees east, and then I went 100 miles south and it was 30 degrees east, the whole magma came up at once. But if the directions slightly change over the distance, or maybe you get a reversal in the middle of the cooling history or something like that, then you know that some time has passed that's not really getting captured by the geochronology, but the paleomag can start to tease that out a bit.
You are a Basil Tikoff student?
Yes, I am. I am kind of between my master's and my PhD right now, so I just finished my second year of grad school, and I'll hopefully be defending my master's in October sometime.
Okay, good. This is how many field seasons in a row already for you out here in Idaho?
So this is my third summer where I've probably only spent like a week or two at home in Wisconsin.
Yeah.
But the rest of it, I've been pretty fortunate and been able to spend a lot of it out west doing various bits of my own field work, but then also field camps and some other awesome places.
Is your PhD work on the Western Idaho Shear Zone?
I guess tangentially,
Okay.
yeah. So my PhD is looking at a little bit broader regional in sort of Idaho and Montana.
Oh, I guess I didn't know that. So what's the difference between your master's work? That was here.
Yeah.
And what did you do for your master's with this shear zone? And then how are you going to expand out to further afield for your PhD?
Yeah, so for my master's, I'll kind of start with, we had an EdMap grant, and so with that, it's a pretty awesome program they have to get students in the field mapping, and so I was out there, and this is why I spent a lot of time out here, actually mapping a USGS quadrangle, and that was a pretty awesome opportunity, and that quadrangle kind of covers up the southernmost extent of the Western Idaho Shear Zone before it gets covered up with the Columbia River basalts and the Snake River Plain. And the reason we're interested in this is you talked to Sarah Trevino, and she was working on a shear zone in sort of Nevada, and there's been a lot of other students, Neas Torres, that was working in like the Sierra Nevadas, that was also looking at some of these shear zones. And so there is kind of this question of how do these all connect, and so that was kind of the interest in this really southernmost extent of it, is just to be able to connect it better to the Owahis and the Nevada and further.
Cool. Are you the person behind Strabo Spot?
No, there are many, many wonderful people behind Strabo Spot. We have an awesome team. Yeah, I do work on Strabo Spot right now. But they've been doing Strabo Spot for a long time, longer than I've been around, that really have put in the groundwork to get it going. So the fancy title is the user interface designer, but it basically means I get to work with the geologists and the programmers and really think through how are we getting these workflows into the application, what is it going to look like, and then working with the programmers to implement that and test it. And that's a really awesome thing because with my own research, it's pretty structurally tectonic focused, but with Strabo, I get to work with a ton of communities. Like I get to work with volcano people and sedimentary people and kind of be all over. And so that's a pretty awesome opportunity.
For those that don't know, what is Strabo Spot?
Strabo Spot kind of has two main parts. There's this digital database for storing structural data. And then, if I'm being honest, kind of the fun part is our digital field notebook. And so we have an application that you can use in the field to take measurements, take notes, take photos, upload it all to our server, and then you can make this data public and share it with others. And that's kind of the idea is moving forward, is we can have these really large data sets to try and piece together some of these ideas that are really large and you can't really work on as one person, and to be able to bring some of that data together.
Sweet. Well, you're not just attending this Penrose Conference, you basically are putting the thing up. I mean, it's you, right? You're Basil, but you're a leader of the conference at age whatever.
Yeah.
Were you asked to do that? Or did you volunteer? Like, this is a major logistical thing as well as the academic part of it.
Yeah, so I mean, a part of it is that I did do my master's here in, well, not exactly here, but in the Western Idaho Shear Zone to the south of here. And so I do have some familiarity with the area, and so the opportunity to kind of get this behind the scenes look and think about it a little bit more has been pretty awesome. But then I'll be pretty honest I do enjoy this sort of I'm trying to think of the nicest word, the excitement and all that goes with it of kind of bringing these conferences together and bringing all these people together. I think it's a really cool opportunity, especially like you mentioned at sort of this stage of my career, to get the behind the scenes look at it and not really have so much pressure on myself, so that maybe in the future it's not so just being dropped in and trying to lead my own. But
right.
Yeah, so it's a pretty cool opportunity.
Well, I mean, you are essentially a colleague of Basil and Station, as far as I can tell. You're not a grad student who's just doing the minimal stuff. I mean, they're leaning on you, they're asking you for advice. I mean, I'm impressed.
Well, that's very kind of you, but yeah, it's definitely a group effort, and then we have a lot of others. So there's a lot of other students from both ends that are helping to keep it all going and stuff. So we've definitely leaned on a lot of people. And earlier in the year, it was pretty awesome because we got to do sort of these field trips with other people who have done a lot of work in this area, and so gone to their field areas with them, and they kind of explained it to us, and so we were able to like type that up in the field guide, and so it was pretty awesome.
Thank you, Ellen.
Yeah, thank you, Nick.
On Wisconsin.
Yeah, on Wisconsin.